Okay, so I'm just going to be working through a bunch of examples. Alright, so for my first example, let's say that we have two vectors, u is 2, 0, -1. Let's say the vector b is 1, 3, and -2. Okay. So I just want to go over like some basic operations on vectors. So you should be able to compute an expression like this, 2u minus b. Okay. So to compute 2u, you just multiply 2 into each component of u. So that'll give you 4, 0, -2. And then we're subtracting b, which is 1, 3, 2. And then to subtract or add vectors, you just do it component by component. So here you'll get 4 minus 1 is 3. 0 minus 3 is -3. And then -2 minus 2 would be -4. Okay? Alright. You should be able to compute the magnitude or the length of a vector. Okay? So recall, if I have a vector u with components u1, u2, u3, the length or magnitude of the vector u, we usually denote it with like a sort of absolute value symbol. The formula, it was the square root of the x component squared plus the y component squared plus the z component squared, okay? Alright, so in this example, the length of u would be the square root of 2 squared plus 0 squared plus -1 all squared, which would give us the square root of 5. Similarly, the length of b would be the square root of 1 squared plus 3 squared plus -2 squared. That's going to give us square root of 14. Okay? So we also had the dot product operation between two vectors. So remember that you can compute the dot product by multiplying the x, y, and z components together, and then adding all of that up. So that's the formula for the dot product. In this example, if we use the formula, so dot product would be 2 times 1, which is 2. And next it would be plus 0 times 3, which should be 0. And the next would be -1 times -2, which would be positive 2. And so ultimately the dot product would be equal to 4. Alright? Okay. We had a formula involving the dot product and the angle between two vectors. Right, so given two vectors u and v, I look at that angle between the two of them. we have this formula that the dot product between u and v is equal to the length of u times the length of v and times the cosine of the angle between the two vectors. Okay, so if I wanted to solve for the angle theta between my two vectors in my example, well, we know that the dot product is 4. The length of u was square root of 5. The length of v was square root of 14. So if I wanted to solve for theta, let's see here. So this is square root of 5 times 14 is 70. So I'll divide that to the other side. So we get 4 over root 70 equals cosine theta. And if I want to get theta, I would apply the inverse cosine to both sides. And then that would be my answer for theta, okay? All right. Now, one consequence of this formula is the following fact, that two vectors u and v are orthogonal to each other. If and only if their dot product is equal to 0. Okay? So in this example, the dot product between u and v was not 0, and so therefore they are not orthogonal to each other. Okay. So next I also want to talk about the notion of projections. In particular, we distinguish between the vector projection and the scalar projection. Okay, so let's draw two vectors. Okay, let's say this is vector v, and this is vector u. So in this picture here, if I drop a perpendicular down from u onto the line determined by the vector v, okay, so that would be a right angle. Okay. Then this vector here that I'm drawing in green, that green vector is what we would call the vector projection of u onto v. And there was a formula for this. So the formula for the vector projection of u onto v, actually first some notation. So I'll write it like this: projection of u onto v. All right, and the formula for this, it's dot product between u and v divided by the dot product of v with itself. So all that is a scalar, and then times vector v, okay? Now there's a couple other ways of writing out this formula. So remember that a vector dot product with itself gives you the length of that vector squared. So here is another way of writing out the same formula. And then another way that you can write out the formula is this. So what I'm going to do right now is, in my denominator, I'm going to take the length of v, and I'm going to pull one of them outside of the parentheses and put it beneath the vector v, okay? Okay, so when I do that, what happens is this over here is a unit vector. Unit vector is a vector whose length is equal to 1, all right? So there I have a unit vector pointing in the same direction as v. And then this quantity over here in the parentheses is what we call the scalar projection. Okay. Of u onto v. So because this is a unit length vector, then this quantity here, the scalar projection, would represent the overall length of this vector up to a plus or minus sign. All right. So that's kind of the significance. The scalar projection acts as, or it is the length of the vector projection up to plus or minus sign. Okay. And then just a quick example. So again, I'll just make up two vectors real quick. Let's say this is u. Let's say this is v. So if I want the vector projection, okay, of u onto v. So using this formula over here for the vector projection, I'm going to do the dot product between u and v. So dot product would be 2 plus 0 minus 6. It'll be all over v dot product itself. So it'll be 1 squared plus 0 squared plus 3 squared. And all of that will be times the vector v. So that's going to be negative 4 over 10, so negative 2/5 times 103. To me, this is a perfectly acceptable answer. If you wanted, you could multiply the negative 2/5 into the vector, and you'll get negative 2/5, 0, and negative 6/5. Okay? And then if I wanted to get the scalar projection, of u onto v, then using the formula here for the scalar projection, we'll do u dot v, which was 2 minus 6, so negative 4, over the length of v, which was the square root of 1 squared plus 0 squared plus 3 squared, so square root of 10. And that would be the scalar projection, all right? Okay. Next, I want to talk about the cross product. Okay, so if I have two vectors u and v, first just recalling how to compute the cross product. So we set it up as a determinant, put ijk on top, list the components of u, and then the components of v. And in order to compute this determinant, what we're going to do is, starting with I, cross out the row and the column containing I. Then for the remaining 2 by 2, you're going to do sort of like a cross multiply and subtract. So here it's going to be u2 times v3 be minus u3 times v2. Okay. Next, with j, I'm going to subtract that one next. And then for j, if I again cross out the row and the column containing j, and then do what I did before, I'm going to get u1 times v3 minus u3 times v1. And then last for k, we're going to add this one. And do the same thing, cross out the row and the column containing k. Then we're going to have u1 times v2 minus u2 times v1. Okay? So let's just do a quick example with numbers. So let's take u, let's take v. Okay, so the cross product between u and v So computing this, it's going to give me, let's see here, so let's copy down I. And then we're going to have 1 minus 0, which is 1. Then we're going to have minus j. And then for j, cross those out. I'm going to get 1 minus 0, 1. I'm going to have plus k. And then cross these out. And then I have negative 3 minus a negative 2. So negative 3 plus 2 would be negative 1. So we get the vector 1, negative 1, and negative 1. And that would be the cross product, okay? So the cross product has some very important properties, so I'm going to go over those. Okay. So probably the most important property for us is that the vector, the cross product, u cross v, is orthogonal to both u and v. Okay, that's probably the most important property for our purposes. You can confirm in this example the dot product between u and u cross v is 0. Likewise, the dot product between v and u cross v should also be 0. And so therefore you can see that the cross product is orthogonal to both u and v. And this is a good way of checking your answer. If you want to know if your cross product was correct, check if it was orthogonal to u and v. All right, some other properties. So the length or the magnitude of the cross product is equal to the length of u times the length of v times the sine of the angle between the two vectors. And this has a sort of a geometric significance or a geometric interpretation. This is also equal to the area of the parallelogram determined by u and v. Okay? So in other words, if this is u, that's v. Here they form a parallelogram. And so the area of this parallelogram would be equal to the length of the cross product. All right? Now notice that if instead of the area of the parallelogram, if I wanted the area of this triangle determined by u and v, the triangle is half of the parallelogram. So therefore, we can also say that the area of the triangle determined by u and v, that would be equal to 1/2 the area of the parallelogram. So it would be half the length of the cross product. Okay? And then thirdly, regarding the direction of the cross product, we know that it's orthogonal to u and v. The direction is determined by the so-called right-hand rule. Okay. All right, so I'm going to edit in a video of me explaining the right-hand rule. Okay, so here I'm going to edit in a quick video about the right-hand rule to determine the direction of the cross product. So I have a picture here, or sorry, I have on the board here, picture of two vectors u and v. All right. So to determine the direction of u cross v, what I want to do is take my index fingers. I'm going to point them in the direction of the first vector, so u. Now, I can either point my fingers this way, or I can point them this way, all right? I want to point them in the way so that my fingers will curl towards the second vector. So if I want my fingers to curl towards v, I want my hand oriented like this, so that my fingers will naturally curl towards v. So if you point your fingers this way, they would still curl towards v, but that's taking the longer route. So you want to choose the orientation so that you can curl your fingers like towards the shorter route, if you will, to get to v. Okay. So I guess between the smaller and the bigger angle, your fingers should curl towards the smaller angle. Okay? So I'm going to point my fingers in the direction of u, the curl towards V. The direction of my thumb tells me the direction of the cross product. So U cross V will be pointing out of the board. So it would be perpendicular to both U and V, as we talked about earlier, okay? For some extra practice, if I want to do V cross U, okay, so the order matters. If I'm doing V cross U, I would point my index fingers in the direction of V. And I want to do it in a way so that my index fingers will curl towards the vector U. If I curl them, I want my fingers to curl towards U in the direction of the smaller of the two angles between V and U. So if I curl them this way, my thumb, if you guys can see it, it naturally points into the board. So hence, the direction of V cross U is actually going to be into the board, all right? So just kind of a quick recap on the right-hand rule. Point your fingers in the direction of the first vector. They should curl in the direction of the smaller angle towards the second vector. And then the direction of your thumb, well, the direction your thumb points in would be the direction of the cross product, okay? So this, I think it's not too important, but I will note it is true that V cross U will turn out to be the negative of U cross V. So same magnitude, but they'll just be in the opposite direction, all right? And then one more thing is there's something called the, well actually, yeah, I'm not sure. So let's just go back to the example that we did where we computed the cross product. Okay. So using the numbers that I have up here, so the area of the parallelogram determined by U and V. So it's the length of the cross product. And the cross product was 1, -1, -1. So the magnitude is square root of 1 squared plus -1 squared plus -1 squared. So it would be square root of 3. Okay? And then quickly, I just want to mention the scalar triple product. Okay, so this is an operation involving 3 vectors, u, v, w, all right? And the formula for the scalar triple product is u dot product with v cross w, okay? So the significance of the scalar triple product is that it represents the volume of the parallelepiped, all right? Volume of the parallelepiped determined by U, V, and W, okay? And then just a quick picture. So it's the volume of the parallelepiped up to sign. So the scalar triple product might be negative. If so, the volume would be the absolute value of it. Okay? And then just a quick picture. So if this is U, that's V. And then if that's W, so the idea is these three vectors form what we call a parallelepiped. Okay, so that's my picture of the parallelepiped determined by the vectors U, V, and W. All right. So just an example. So I'll make up three vectors. Let's say U is 1, 2, 0. V is 0, negative 1, 3. Let's say W is 1, 1, 3. Okay, so the volume of the parallelepiped determined by UVW so using the formula for the scalar triple product, it's U dot product with V cross W. Alright, so let's compute the cross product between V and W first. Oh, and I'll tell you what, volume will be the absolute value, so I'll just put absolute value there. Okay. So let's do the cross product of V and W real quick. So that's going to be, looking at the first component, negative 3 minus 3. Next will be the negative of 0 minus 3. So it'll be positive 3. And last will be 0 minus negative 1 plus 1. Okay? Alright. So then here I'm going to do the dot product between U and V cross W. The dot product would be negative 6 plus 6 plus 0. And so actually we get the answer 0. So that means that since the volume of the parallelepiped is 0, that essentially means that W is in the plane determined by U and V. So you can say that the vectors are coplanar. Okay, so the parallelepiped has no height, if you will. You can think of it like that. Okay. Let's talk about lines next. So lines in R3. So let's say I have a line L in 3 dimensions. Let's say the line passes through this point, which I'm going to call P. And let's say we have a direction vector V, which lies along the line L. Okay? Then the so-called vector equation of L, which is also known as a parameterization of the vector L. Okay. So it is a vector valued function, R of t, equal to the point P plus the vector V times t. Okay? So this was the form of the so-called vector equation of the line L. The vector equation is just a parameterization of the line. And I don't like equal, so I'm going to do parentheses. Okay? Okay. Now, if the components of P are P1, P2, and P3, and if the components of V, actually, let's do, I think I'm going to write it like this. This looks better. So if the components of P are x naught, y naught, z naught, and if the components of V are A, B, C, then taking the vector equation, if I write out the components, then we can add all of this up. And so if we do that, we'll get x naught plus AT, y naught plus BT, and z naught plus CT. Whoops. So this would be the vector equation written out in terms of the components. From the vector equation, if we write out the x, y, and z components separately into three equations, x is x naught plus AT, y is y naught plus BT, and z is z naught plus CT. These three equations together form what we call the parametric equations of the line L. So these are sort of different ways of trying to describe a line in R3. You can see that they are equivalent to each other. So you can easily go from vector equation to parametric equations. If you have the parametric equations, you can easily write out the vector equation. Okay? Now, we have another way of describing lines in R3. Those were the symmetric equations. Okay? So to obtain these symmetric equations, what you do is take the parametric equations and in each equation solve for t. So in the first equation, if you solve for t, you'll get t equals x minus x naught divided by a. In the second equation, if you solve for t, you're going to get y minus y naught over b. In the third equation, solving for t, you get t equals z minus z naught over c. So because all three of these are equal to t, we can set all of them equal to each other. And that gets us the symmetric equations of the line L, all right? So I'll do a couple of examples. Okay, so let's say we're given the symmetric equations of some line which I'm going to call L. Let's say the equations are x equals 2 plus t, y equals negative 3 plus 2t. Say z is 5 minus 4t. Oh, whoops, these are parametric equations. That's my bad. Let me redo that. So we're given symmetric equations. Let's say they are x minus 4 over 3 equal to y is 2 plus 2 over negative 2. This 2 equals z minus 1 over, let's just do z minus 1. Okay? So let's say we're given the symmetric equations of some line L. We want to find a vector equation for the line L. Okay? So I talked about how to go from vector equation to the parametric equations, and how to go from the parametric to the symmetric. So in my example, I'm now going to illustrate, how to go backwards. So starting with the symmetric equations, we can get the parametric equations by doing the following. I'm going to take each part of my symmetric equations and set it equal to t. And then I'm going to solve for x, y, and z in each equation. So here you get x is 4 plus 3t. Here you get y is negative 2 minus 2t. Here you're going to get z is 1 plus t. So this gets us the parametric equations. Okay? Parametric equations for the line L. Once we have the parametric equations, we can write out the vector equation. So we'll write it as RT equals x is 4 plus 3t, y is negative 2 minus 2t, z is 1 plus t. Okay? And then that would be one acceptable answer. All right. Let's do at least one more example. So say we're given some line, and what we're given is that it passes through 2 points. Let's say it passes through the point 2, 1, 3, and negative 1, 1, 0. And then what we want to do is find a vector equation for the line. So remember, the vector equation has this basic form. It's a point on the line plus, and then we need a direction vector, and then times t. So in order to get the vector equation, we need two pieces of information, the point and the direction vector. Now we already have more than one point on the line, so we already have multiple choices for p. What we need to do is we need to find a direction vector for the line. So most problems which involve finding the vector equation of a line will involve using the information given to find a direction vector. So in this problem, here's the idea. We have 2 points, which I'm going to label A and B. Another line passes through those 2 points. So if I take the vector connecting the 2 points like that, that would be a suitable direction vector for our line. So that's going to be the strategy for B. We're going to take it to be the direction vector from A to B. Now, if you remember, to get that direction vector connecting 2 points, you subtract final minus initial. So if I do B minus A, we're going to get -3, 0, -3. Okay? So now we have a direction vector. For the point P, we could use either of these 2 points. I'm just going to use the first one. So then writing out my equation, I'm going to have the point, which I'm going to use A for the point. And then for my direction vector, I'm going to use -3, 0, and -3. And then times t. Okay? Now, if you used B instead for your point, that would be an acceptable answer. So there's more than one right answer when you're trying to find the vector equation of a line. Okay. So I am going to, okay. I'm going to, okay, let's move on. So I'm going to talk about planes next. Okay, so I had to take care of something real quick, but I'm back. So talking about planes now. Okay. Oh, whoa. Okay, let me fix that real quick. So in order to write out the equation of a plane, we need 2 pieces of information. We need a point that lies on the plane, and then we need a normal vector for the plane. So let's say I have a normal vector with components A, B, C. And then this point on the plane, let's say it has components x0, y0, z0. Then we can write out the equation of the plane in the following form: A times x minus x0 plus B times y minus y0 plus C times z minus z0 equals 0. Okay? Okay, now if I distribute A, B, and C, so here I have my AX, my BY, and my CZ terms. For the other terms, minus AX0, minus BY0, and minus CZ0, I'm going to move all of them over to the other side. They all become plus when I do that. And all this is just a constant, so if I just call it D, then we can also write out the equation of a plane in this form as well. Okay? So these are 2 ways of writing out the equation of a plane. So typically I use the first form, and if I feel like moving everything over, then I can, and then I will leave it in this form. Okay? So let's do at least one example. So let's say we want to find the equation of a plane And let's say we know that this plane passes through the point, let's just do 1, 2, 1, passing through this point. And let's say we also know that the plane is also orthogonal to the line given by this vector equation, 2, 5, negative 3, plus 1, 2, and negative 3, t. Okay? All right. So again, to write out the equation of a plane, you need two pieces of information, a point on the plane and the normal vector. Most of the problems involving finding the equation of a plane involve using, or they boil down to, using the information given to find a normal vector. So let's see how to do that in this problem. Okay? So we already have a point on the plane, 1, 2, 1. So we just need to find the normal vector. Now, what we know is that we have this line which is perpendicular to the plane. So it might look something like this, makes a right angle, like that. And we have a point that is on the line, and then we also have this direction vector. So that direction vector, as we know, is a vector which lies along the line. So hence you can see that this direction vector for the line is also a normal vector for the plane. Okay? So therefore, we can use that for the normal vector. So then just writing out the equation of our plane. Okay, so the normal vector gives us the A, B, and C. So I'm going to have 1 times x minus, here the point on the plane, x naught, y naught, z naught. So x minus 1, and I'm going to have plus 2 times y minus 2. Then we're going to have minus 3, z minus 1 equal to 0, okay? So that should be an acceptable answer. If I want to simplify, then I will move my constants to the other side of the equation. So here we have minus 1, minus 4, it's minus 5, and then plus 3 would be minus 2. When I move it over, it becomes positive 2. Okay? All right, good. So another example. Let's say I want to find the equation of a plane. Passing through points 1, 1, 0, 2, negative 1, 1, and 0, 1, negative 2. Okay? Okay, so we have plenty of points to choose from, which lie on the plane. Again, what we need is a normal vector. So here is going to be our strategy for the problem. We're going to compute the direction vector from A to B, as well as from A to C. So a normal vector to the plane would have to be orthogonal to both of these two vectors. And so if we want a vector which is orthogonal to both of these two vectors, the natural choice is to use their cross product. So for our normal vector, we're going to take it to be the cross product between the vectors AB and AC. Okay, so let's see here, AB. So remember, we got the direction vector AB by doing B minus A. So B minus A is going to give us 1, negative 2, and then 1 minus 0 is 1. AC, we get that by computing C minus A. So C minus A will be negative 1, 0, negative 2. Alright, setting up our determinant to get the cross product. So we're going to do 4 minus 0 is 4, minus, we're going to have negative 2, minus negative 1. So negative 2 plus 1 is negative 1. And finally, we have 0 minus 2. So therefore, we get the vector 4, 1, negative 2 for the cross product. So that gets us the normal vector, which would be the ABC in the equation of the plane. For a point on the plane, let's just choose A. And then using those two pieces of information, writing out the equation. So it's going to be A times X minus, I'm going to use A for X naught, Y naught, Z naught, X minus 1. Next we have plus B times Y minus Y naught. And then we have plus C, so minus 2 times Z minus Z naught, which would be 0. And then equal to 0. If I want to simplify it, we get 4x plus y minus 2z. And here I have minus 4, minus 1, so that's minus 5. Move it over, comes positive 5. Okay? Alright. So when you're trying to find a normal vector to the plane, oftentimes if you can get two direction vectors in the plane, then you can cross them to get the normal vector, okay? Okay, so next we're just going to talk about curves in 3D. So we already talked about lines in 3D. And so now we're just going to generalize that to any arbitrary curve. So curves in R3 are going to be described by a parametrization, similar to how lines were. So the parametrization is just like a vector value function. It'll have, an x component, a y component, and a z component. Okay. So let's just look at a quick example. Okay, so let's say for this example, I'm going to have -2 sine t, 3 cosine t, and let's do 5 minus t. Okay, so let's say I want to get a sketch of this curve indicating the direction as well, okay? Alright, so how to get a sketch of this curve. So first, if your curve has like sines and cosines in it like this, what I recommend is the following. Okay, so looking at these two equations, so if we were in 2 dimensions, you might recognize that this gives us a parametrization of an ellipse, okay? That would be if we were in 2 dimensions, all right? Just for those of you who can't see that, I will just very quickly show you how you can see that. So if I take these two equations, if I divide the coefficients to the other side, you will get -x/2 is sine t. You will get y/3 is cosine t. And then what I'm going to do is, I know that we have this trig identity that sine squared t plus cosine squared t equals 1. So if I replace sine with -x/2, sine squared would be x²/4. Cosine squared would be y²/9. And then that should be equal to 1. So you guys might recognize this as being the equation of an ellipse in 2 dimensions. Okay? So this is an ellipse whose radius in the x direction would be 2, all right? So this coefficient tells you like the radius of the ellipse in the x direction. Similarly, the radius of the ellipse in the y direction is going to be 3. So this would be what the ellipse looks like in 2D, okay? Now, however, we are in 3 dimensions, so we do have a z-coordinate. So remember that in 3 dimensions, this would actually be the equation of an elliptical cylinder instead. okay? Okay, so this is not entirely necessary, but I think it's good to see, so I'm going to draw it. Okay, so the elliptical cylinder would look something like this. So we have this ellipse, which I'm drawing in the xy plane. And then basically it just stretches upwards and downwards as well, okay? All right. So the fact that x and y satisfy this equation, it tells me that the curve lies on this cylinder, okay? All right. Now, if I want to try to imagine what this curve is doing, so let's plot a couple of points. So I'm just going to plug in, I think I'll plug in 3 values of t. So I'm going to plug in t equals 0. Let's pick some nice values. Let's do pi over 2 and pi. Let's figure out what x and y are. So if t is 0, looks like x will be 0, y will be 3. T is pi over 2, x will be negative 2. Y is going to be 0. When t is pi, x will be 0. Oh, whoops, I forgot z. Let's see here. When t is pi, y will be negative 3. Z would be, 5. 5 minus pi over 2 and 5 minus pi. Let's try to plot those 3 points. So let's say this is at a height of 5. So when t is 0, we're at the point x is 0, y is 3, z is 5. So it's going to be like right above y equals 3 down here. At t equals pi over 2, we're at x is negative 2, so we've gone backwards. Y is 0. Z is 5 minus pi over 2, which is still positive, so we're kind of behind the ellipse. So we've kind of gone, we're traveling along the back of the cylinder right now. And then when t is pi, x is 0, y is negative 3. So we've traveled back here now. And z is 5 minus pi, so we've descended further downwards. Okay. So we have a curve on the cylinder, moving around, kind of going like this. That's the direction so far, okay? So if we continue, what's going to happen is, so t is the angle. So as we're moving around, what's happening is t is also affecting the height or the z-coordinate. So as we move around the cylinder, we're also descending downward is what's happening, because z is decreasing. So if we continue, it's going to kind of keep going like this. Like that. So it's going to be an ellipse, or sorry, not an ellipse, but a sort of helix, okay? So that's a rough sketch of our curve. Okay. So it helps if you see cosines and sines. That keys you in that your curve likely lies on a cylinder, possibly circular, possibly elliptical. Okay. Okay. So continuing to talk about curves. So next, I'm going to talk about the tangent line to a curve. So let's say here I'm just going to draw some arbitrary curve. Let's say this is the direction. Let's say that RT is a parameterization of this curve. Now at this point here, okay, so let's say that point is given by R of T naught, okay? So I like to think of the parameterization of a curve as representing the position of some particle. So T would be the time, all right? So essentially we're saying this would be the position of the particle at time T naught, okay? Now if you're thinking of R of T as representing the position, position at time T. So you guys might remember that the derivative of the position function gives you the velocity. Similarly, the second derivative gives you the acceleration, although I won't be using it, okay? But I'll just remark on that. So the derivative, if I were to draw it in the picture right now, well, you can see that the particle is moving this way. So at this point, its velocity is kind of along this direction, okay? All right, so this derivative or velocity vector is tangent to the curve at this point. So if I want to write out the equation of the tangent line, okay? Well, we know that to write out the vector equation of a line, we need a point on the line and a direction vector for the line. So R of T naught, that is the point or a point that lies on the tangent line. So we'll use that for our point. And then for our direction vector, well, the derivative or the velocity vector is tangent to the curve at this point. Hence, it will be a direction vector for the tangent line to the curve at that point, okay? So we'll use R prime, the derivative for the direction vector. Okay. So this will kind of be the general form for the vector equation of the tangent line to a curve. So let's look at an example. Okay, so let's say here I am just going to write out a parameterization for some curve. Okay. Let's say I want to find the tangent line to this curve. At the point 1, -3, and 1. Okay? All right, so we have the point right now, so we have the r(t0). What we need is the direction vector or the tangent vector. So we're going to need the derivative. Let's just compute that first. So to get the derivative, you just do it component-wise. Okay? Now, we do need to know what time to plug into the derivative to get the tangent vector at this point. So therefore, we need to know at what time are we going to be, let's say at what time is our position going to be at this point, okay? So we need to know when our position rt is equal to 1, -3, 1. So to do that, we can just take the x, y, and z components of our position. We're going to set it equal to this point, 1, -3, 1. And then we basically just need to solve for t, all right? This one's probably the easiest one. Well, maybe not, but e to the t is 1 only when t is 0. Okay. Sometimes it's more difficult to solve, but you want to solve the system of equations to find t. So here we have t is 0. So therefore, I want to get the tangent vector at this time. So I'm going to plug in 0 to the derivative. That gets me the tangent vector 0, 2, 1. Okay? Okay, so then we have the point on our tangent line. Here is a direction vector for the tangent line. So now I'm just writing out the vector equation of the tangent line. So I'll write it as L of t equals the point 1, -3, 1 plus the direction vector 0, 2, 1 times t, okay? All right. Next, I want to talk about arc length. So just continuing the discussion on curves, we'll talk about arc length next. All right, so let's say I have some curve moving in this direction. R of t is some parametrization, and this segment of the curve is the segment of the curve where t is between a and b. So if we want to calculate the length of this segment, which is the arc length we call it, the formula for the arc length is the integral from a to b of the magnitude of the derivative vector, okay? So just a quick example of this. So let's say our curve RT is given by let's do sine of 3t. Let's do t squared, and let's do cosine of 3t. Okay? And let's say I want to get the arc length. Oh, let's see here. Instead of 3, let's do high t. I think that will work nicer. Okay. And let's just say I want to find the arc length with t between 0 and 1. So to do that, I'm going to compute the derivative. Okay, let me think. Okay, I'm also going to change the middle, so instead of t squared, let's do 2t to the 3 halves. That should work out more nicely, okay? Alright, so for the arc length, first we need to compute the derivative. So derivative of sine pi t would be pi cosine pi t. Next, we're going to get 3t to the 1/2. Derivative of cosine is negative sine. Okay, so that is the derivative. Now to get the arc length, we need the magnitude of the derivative vector. So let's compute that next. So magnitude is the square root of the x component squared plus the y component squared plus the z component squared. Okay, so we can simplify this a little bit. If I take these two terms, if I factor out a pi squared from them, we're going to get cosine squared pi t plus sine squared pi t. And remember, cosine squared plus sine squared will simplify to be 1. So we just have pi squared plus 9t. All right? So then to get the arc length, the formula is going to be integral from 0 to 1. Magnitude is the square root of pi squared plus 9t dt. All right. So to evaluate this integral, we'll do a u substitution. We'll just let u be pi squared plus 9t. Then du will be 9 dt. So we can see dt is 1 over 9 du. So we're going to get, replace dt with 1 over 9 du. And then we have square root of u. So square root of u is u to the 1/2. So integrating, we're going to get u to the 3 halves divided by 3 halves. So then, dividing by a fraction, we multiply by the reciprocal. And then I'm going to replace u with pi squared plus 9t. And then we also need to evaluate from 0 to 1. So we're going to get 2 over 27. Okay. If we plug in 1, we get pi squared plus 9 minus what we get when we plug in 0, pi squared. Pi squareds cancel. 9 over 27 gives us a 3 in the denominator. So it looks like we get a final answer of 2/3, okay? All right, and I will pause for a moment and I will resume later. Okay, so I'm just going to do a couple more examples now. So talking about partial derivatives. Now I have to say I'm not 100% certain what the topics are on your first exam. I saw on the practice exam there were some questions about partial derivatives and the tangent plane and things like that. So just in case that will appear on the exam, I am going to cover them in this video. But I'm not sure if these topics will actually be on the first exam this semester, all right? And let's just do a simple example of computing some partial derivatives. So here I'm just going to create a function. Okay, just a really simple one. So the idea of partial derivatives, first there's two notations in use. So here this represents the partial derivative of f with respect to x. And as sort of a shorthand notation, we also write it as f subscript x, okay? So the way this works is you compute the derivative treating x as a variable, and you treat all the y's as if they were constants. Okay? So here, if I'm doing the derivative with respect to x, I know the derivative of x squared is 2x. The y is a constant, so it's just going to carry over. Derivative of 3x squared will be 6x. Now for the derivative of y squared, be careful if you're doing it with respect to x, then we're treating the y squared as a constant, and derivative of a constant by itself would be 0. And then likewise, derivative of 4 would be 0 as well. So ultimately, the partial derivative with respect to x is simply 2xy minus 6x. If I want the partial derivative with respect to y, so again, f subscript y is in alternative notation. So now, with respect to y, we treat y as the variable, and we pretend that x is a constant. So here, the derivative of y is just 1, and x squared is a constant, so it just carries over as a multiplier. Again, treating x as a constant, derivative of all of this would be 0. Derivative of y squared with respect to y is 2y, and then derivative of 4 will be 0, okay? All right. So these are what we call the first order partial derivatives. So of course we can compute the derivative more than once. So we can look at the second order partial derivatives as well. So to get the second order partial derivatives, you can take fx and differentiate fx with respect to x. So the notation for that is this. Alternative notation is fxx. So this is taking the derivative of fx with respect to x. So if we do it with respect to x, we're treating y as a constant. So derivative of 2xy with respect to x is just 2y. And then we have minus derivative of 6x with respect to x will be 6, okay? Now we can also take fx and then compute its partial derivative with respect to y. So the notation for that would be f subscript xy or d2f dy dx, all right? So here's fx. If we do the partial derivative with respect to y, then derivative of 2xy will be with respect to y, 2x. And then this is all constant with respect to y, so derivative would just be 0. Now we can also take fy and differentiate fy with respect to x. Then we can also take fy and differentiate it with respect to y. So here are the different notations for each of them. Okay. So in my example, here's fy. So with respect to x, it's going to be x squared plus 0, okay, with respect to x. Oh, sorry, whoops. Yeah, so derivative with respect to x would be 2x. And then with respect to x, this is constant, so the derivative is 0. Okay. And then for the derivative of fy with respect to y, that'll be 0 plus 2. So it'll just be 2, okay? Now, notice that fxy and fyx happen to give the same result. And so in this class, that should pretty much always be the case for all of the functions that you encounter. So actually earlier when I wrote down x squared, I knew I made a mistake because I saw that these two were not equal to each other. All right. So in this class, fxy and fyx should always agree with each other. And this represents all of the second order partial derivatives of our function. Okay. All right, so I won't do any more complicated examples, but just be wary of possibly needing to use the product rule or the quotient rule or the chain rule when you are computing these partial derivatives, okay? All right. Now just like a little bit of some of the applications of partial derivatives. So we can use partial derivatives to get the tangent plane to a surface. All right, so let's say I have some surface. Let's draw something like this. So imagine I have a surface, and let's say this surface is the graph of some function f of xy. Okay? I'll go ahead and draw my xyz axes. Okay. And so let's say at a certain point, x naught, y naught, we have this point up here on the surface, and then you can imagine drawing a tangent plane to the surface passing through that point, all right? All right. And to get the equation of the tangent plane, so we can write the equation of the tangent plane like this: z minus f of x naught, y naught equal to the partial derivative with respect to x, at the point x naught, y naught, then times x minus x naught, and then plus partial with respect to y, evaluated at x naught, y naught, and then times y minus y naught, okay? So to recap, if you have a surface, which is the graph of a function of f of xy, you want a tangent plane at some point x naught, y naught, and the z coordinate of this point up here would be f of x naught, f of y naught, okay? Then you can write out the equation of the tangent plane in this form, okay? So let's just do a simple example. Okay. So if we want to find the equation of the tangent plane to the graph of the function f of xy equals let's do x squared e to the xy, and we want the equation of the tangent plane to the graph at the point, let's say x is 1, y is 0, and if I want the z coordinate, remember the function represents the z coordinate, so if I plug in 1 for x and 0 for y, you should get 1 times 1, so it'll be 1 for the z coordinate, okay? So we have our x naught, our y naught, and then the z coordinate is f at x naught, y naught. What we need is the partial derivatives. So let's compute those two real quickly. Okay, so fx. All right, so if we do the derivative with respect to x, this is going to be a product rule. So I'm gonna, because it's a product of two functions of x. So the way I do product rule, I do derivative of the first times the second plus the first, and then for the derivative of the second, so remember the derivative of exponential, copy it down, and then multiply by the derivative of the exponent. We need the derivative of the exponent with respect to x. So derivative of xy with respect to x would be y. Guess I don't need parentheses, so just times y. Okay? Now likewise, the partial derivative with respect to y. Okay, so now this time I don't really need to use the product rule, because if I'm doing the derivative with respect to y, x squared is just a constant. And then derivative of e to the xy will be e to the xy times the derivative of the exponent. Derivative of the exponent with respect to y is just x. Okay? Now let's take the partial derivatives and let's plug in the values of 1, 0 for x and y. So if we do that, we should get fx is 2, I believe. And we plug in 1 for x and 0 for y. Looks like fy is 1. So then, to get the equation of the tangent plane, at this point, it's going to be z minus our function evaluated at x naught, y naught, which happened to be 1, equals, and then fx, which is 2, times x minus x naught is 1, and plus partial with respect to y is 1, and times y minus y naught was 0. Okay. All right, and then people often like to solve for z. So I'm just going to move the minus 1 over, so I'll write it as z is 1 plus 2 times x minus 2. And let's just do plus y. And if I want to simplify more, I might distribute the 2. So maybe we can write it as negative 3 plus 2x and plus y. All right? Okay. And then the last thing I'm going to talk about is these so-called differentials. Again, I don't know if this topic will actually be on the first exam. I believe I did see one question about this, though, on one of the practice exams. Now, just quickly talking a little bit about what the differential is or what it's supposed to represent. So here I'm going to go over a little bit of the concept, just a little bit. So I'm going to, drawing 3D pictures is hard, so I'm going to draw a picture in the xy plane. So now imagine we have this curve here, the graph of some function f of x. At this point, I can draw the tangent line to the curve at that point. It'll look something like that. And let's say that the equation of this tangent line, well, you can actually work out what the equation is. It's So say if this is at some point x naught, the y coordinate would be f of x naught. Okay? So remember that the equation of the tangent line if we use a point slope form for the equation of a line, we'll have y minus y naught is the slope. Remember the slope of the tangent line is the derivative of x naught. Slope and then times x minus x naught. By the way, you'll notice this is very reminiscent of the equation of the tangent plane. Only difference is we have two derivatives on the right-hand side, and you have z on the left-hand side. Okay. But anyways, so if I move the f of x naught over, I get y equals this, and instead of writing y equals, I'm going to give this function a name. I'm just going to call it L of x. So this function here that I wrote down is often called the linearization of f at the point x naught. And the linearization is basically the tangent line, or if you will, the tangent line is the graph of your linearization, okay? And so the idea is that, like, what is the linearization useful for? Notice in the picture how near this point, the tangent line and the curve are nearly indistinguishable. Okay? So what's happening is for values of x that are close to the point x naught, okay, your linearization will be roughly the same as your function at x, okay? So here are these two squiggly lines I'm using for is approximately equal to, okay? All right. So that's sort of like one of the ideas or applications of tangent lines and similarly tangent planes is that they serve as a good linear approximation to your function near that point of tangency. Okay? So I can generalize this. So for a function of two variables, okay, the linearization of some function f of xy at some point x naught y naught. Okay? So it will be a function of two variables as well, x and y. And basically, the linearization is just going to be, if I can fit it, okay. Basically, it's going to be the equation of the tangent plane. I'm just going to move the f of x naught y naught over to the other side. Instead of writing z equals, I'm just going to write L of xy equals instead. So it's going to be f of x naught y naught, and then plus fx evaluated at x naught y naught times x minus x naught, and then plus fy at x naught y naught, times y minus y naught. Okay. So that's the formula for the linearization of a function of two variables at the point x naught, y naught. It basically comes from the equation of the tangent plane, all right? And the idea is that if xy is near or close to the point x naught, y naught, then this linearization at xy should be approximately equal to your function at xy. Okay? Now, this expression here, okay, that is commonly denoted as just dz. And we call this the, I guess, the differential of f. Differential of f. Maybe at the point x naught, y naught. That sounds about right to me. Okay. So if we have that L of xy is approximately equal to our function, and let me rewrite this differently. So let me write this out more explicitly. I'm going to write it out as f of xy is approximately our linearization. And for the linearization, I'm going to plug in the expression for it, just f at x naught, y naught, plus, and then all of this, I'm just going to write dz for everything else, all right? So therefore, if I just maybe, move the f of x naught, y naught over to the other side, so that kind of tells you what the differential represents. So the differential of f is representing the change in values between some point xy and some other point x naught, y naught. All right? So since the function, we regard it as representing the z-coordinate of a point on the graph, this difference is often denoted as delta z. So change in z, that is the change in your function at two different points. And we can approximate this change in z by computing the differential, okay? All right, so I'm gonna just quickly set up one example, and I think I will finish my review after that. So I'm gonna make up a function of two variables right now. Let's do x, 2xy squared minus xy plus x cubed. We'll do minus y squared. Not super important. Okay. So let's say I want to get the linearization of f at some point. Let's do at the point 1, 1. So those would be my values of x naught and y naught. And then let's say if I want to use the linearization to approximate my function, at the point 1.1 and 0.9. Okay. And then if I want to, well, I'll do it two ways. So before that, I'm going to write this. So compute the linearization. Let's approximate difference between our function at the point 1.1, 0.9, and at the point 1, So we want to approximate that change in z. That's where our differential will come into play. And then after that, let's say we want to approximate the actual value of our function at this point 1.1, 0.9. Okay? So all using the idea of the linearization and differentials. So first let's do part 1, part 2, part 3. All right, and so first just getting the linearization. Okay, so I think you guys can see the formula for the linearization. So we need our function evaluated at the point x0, y0, which in our problem, x0, y0 was given to be the point 1,1. Okay, so f evaluated at x0, y0 would be 2 minus 1 plus 1 minus 1, so it'll be equal to 1, okay? We're going to need the partial derivatives. So fx is going to be, with respect to x, 2y squared minus y plus 3x squared. With respect to y, it's going to be 4xy minus x minus 2y. And we need the partial derivatives at the point x0, y0. So we're going to plug in 1 for x and 1 for y. That will give us 4 and 1. Okay? Then the linearization at the point 1, 1. It's going to be f at 1, 1. I'll write out the formula. And plus fx at 1, 1 times x minus 1, and plus fy at the point 1, 1 times y minus 1. So plugging in our numbers, this is 1 plus 4 times x minus 1 plus 1 times y minus 1. Okay? So that gets us the linearization. Then if I want to approximate the change in my function at these 2 points, I can approximate it using the differential dz. Okay? All right, so remember that dz was this portion of your linearization. Okay, so in other words, this would be dz. Okay. So then if I want to approximate f at 1.1, 0.9 minus f of 1, 1, this would be approximately equal to my differential. All right. And our differential is going to be, okay. So we already have the points, x naught, y naught sort of plugged into the differential. So what we need to do is plug in 1.1 and 0.9 for x and y as well, okay? So plug in 1.1 minus 1, then we're going to plug in 0.9 for y. If we compute that, it is, what, 0.4 minus 0.1, so I think it is 0.3. Okay. So then it should be the case that this difference is approximately equal to 0.3. And then to actually approximate our function at this point, then that's where our linearization comes into play. So remember that your function should be approximately equal to your linearization. As long as your xy is close to the point x naught, y naught, okay? And so the linearization, it was 1 plus the differential, okay? So therefore, our function at that point should be roughly equal to 1.3. All right, so just a very quick example of the linearization and differentials. I'm going to end my review with that.